Right, so this has started recording. Right, so I will be recording this, and at the same time, remember the last. So I have uploaded the last week's the lecture that we finished yesterday. I have uploaded to the Google Classroom just the PowerPoint, but not the video lectures. So video lectures should be available by the end of this weekend. So I assume. Right, so let me go back to our new today's section. So let me share this with you. Share screen, right. Right, so I would assume that all of you should be able to see my shared screen. And you will see that we will go into more and more little bit of like calculations and bit of practical things for you. So just to give you an idea that how things are done in astronomy. Right. So this topic is about walking through stars and interstellar matter. And from the topic, I guess you can understand that what we are going to talk today is about. Uh, I mean, once you look at the sky at night, you see all kind of stars, right? But in between those stars, there is space, right? What is inside that? Is there anything there, or is there something that we cannot see? So this is what we called as the interstellar matter, right? So as the name interprets, it's matter between stars, right? So this is what we are going to talk today. And remember from the last lecture, so what we did up to the last week is that about we discuss first we discuss about these different constellations, and then after that we have gone through some of the properties that the stars can have. For example, the brightness and apparent brightness, apparent magnitude, and then absolute magnitude, how to define the absolute magnitude, and then how to find the distance to a nearby star using the parallax method. And then we derived or looked at an equation that relates the apparent magnitude, absolute magnitude, and the distance. And then after that, we talked about the temperature of a star, and then we discussed about the spectrum of a star very briefly, and we talked about how we classify the stars into different spectral classes. And remember that I asked you to remember that there is a classification scheme for stars that goes from O, B, A like that. So I would like that you remember that particular spectral classification, right? So these are like things that normally we would expect from somebody who is doing astronomy that they will remember these basic equations and this spectral classification. And then we talked about the color of a star and why color is important and what is the relation between the color and temperature. And the assignment that you probably see in the Google Classroom is kind of related to the what you have talked up last week. Right now, today what we are going to do is we are going to talk a bit about what we have in between stars, right? What are these things which we called as interstellar matter? The reason is that the next section is we will talk about different life stages of the stars. But now the first thing that we have to talk is the birth of a star, right? How stars form at the beginning. So that's what we will be talking about, and this is like a starting point for that, talking about interstellar matter, right? Now, what we know is that the uh, stars actually do not live forever, right? I mean, once you go outside and look at the star, it will be there for your lifetime. But I mean, it's in actual scenario, these stars do not live forever. So they have a lifetime. So they it's like us, right? So we have a certain lifetime, like 60 or 70 years. So we have a birth, and there is a mechanism for that, and then after that we live and we spend like different stages of our lives, and depending on the decisions that we make, we will go into different paths, right? So that's how some of you made into the university, and some of you may not, and some of you may went into different faculties. Like that, you decide your path, right? The stars are very similar to that. So they will start its lifetime uh, in a similar way from the birth, and then they will, depending on their some of their initial properties, they will go through different paths. But at the end, somehow they will die, right? After millions of years. Now, this lifetime of a star is actually huge compared to our own lifetime, because lifetime of the stars are normally measured in terms of millions and billions of years. Now, this is why we don't feel that these stars are changing, right? Because compared to our lifetime, when you look at a particular star that is up in the sky, it will looks like the same for our lifetime, but it keeps changing uh, in its own lifetime, right? Because like 100 or 200 years is like negligible amount of time for a star to change, right? Now, from the previous lecture, you probably have seen that there are many different kinds of stars with different properties on the sky. And actually what we are seeing is that these different stars, they are spending different stages of their life cycle. So that's why you see these different kinds of stars, right? On a statistical point of view, if you look at a statistical sample of stars, we will expect that we will see that all these kinds of stars, right? If you look at a statistical sample, right, it's like humans, because if you get a sample of humans, let's say, let's just consider our own country. We have kids, and then we have school children, and then the uh, youngers, and then young adults, and then adults, like that. We normally have all these categories, right, with different percentages. So similar, the sky is the similar, sky is very similar. If you look at the stars, they have um, the sky has the stars that spend different stages in their lives, right? Now, the question actually we should have is that in the life cycle of the stars, so they, as I mentioned you, they have an initial birth, or we call that this as the formation of a star. And this formation actually happens out of this interstellar matter. So this is why we talk about interstellar matter as the first thing, right? Most of these stars actually experience a very lengthy period of stability after they form through interstellar matter, and then they will combust, have a mechanism that they will consume their fuel, and then they will die at one point, right? Now, the question that we should always have is, what are the ingredients that these stars are made of, right? Now, this is where the interstellar matter and the stars get connected each other. Now, stars normally made out of raw materials available in the space, right? So this should be obvious now, because stars are in the space, so they should consume or get use of the raw materials available there. So basically, they take all their raw materials from this interstellar matter, which is the matter in between stars, right? From some kind of mechanism. So this matter in between stars. So what we will talk during this lecture is different properties of this interstellar matter, right? After that, we will go into the next section to talk about how this interstellar matter is used to form stars. What are the conditions that is required for a formation of a star, those kind of things, right? Now, let's look at some of the properties of these interstellar material. Basically, the interstellar material is not spread evenly throughout the universe, right? Uh, they are not evenly spread, and but usually you will find those interstellar matter inside galaxies, right? And the composition of this material is very pretty much similar to the composition of the stars and large planets. Now, this is why we can think that all these stars are made of interstellar material. right? Because the composition is somewhat similar for stars and also for the interstellar matter. We go into the next slide, right? Now this is a kind of a picture before we go into the next section, an example of different types of interstellar matter, right? Now this image, so I have explained it in the right hand side. You can see that the image has different, it seems image looks very nice and it has different colors. And let's see what these colors actually means. Now the reddish nebula in this spectacular photograph. So actually the what you see here is a nebula, right? And we will talk about that more. And the the glow that you see here is actually the light emitted by hydrogen atoms. And there are some dark areas. Uh, so these are actually cloud of dust that block the light from stars behind them. Now, for example, uh, these areas, you can see that they are quite dark, that you can't see anything in those areas. These dark areas actually where that you have a lot of dust, and this dust actually blocks the light coming from the stars behind those, so that you will see these dark areas. And this upper part of the picture, somewhere here, that you see this bluish light filled with. So these are actually the light reflected from very hot stars, high temperature stars, right? And if you go to the this side right here, you can see very bright star here. We call this as a supergiant star, and the name of this star is Antares. And this is what you see here as a big red patch right here. And apart from those features, you can also see a star cluster right here on the lower right hand corner. This is in fact a star cluster, and this belongs to a type called globular clusters, right? Globular cluster is actually two types of star cluster. There are two types of star clusters which we will talk in next lectures, and one type is called globular clusters and the other one is called open clusters. And this particular star cluster right here is actually a globular cluster, which means it contains most of the stars that contains inside the cluster are older stars, right? And the name of this one in the catalog is actually M4, and you will see all the information that I have mentioned here in the presentation, right? Now let's look at, and this is kind of just to give you an idea how interstellar matter looks like, right? So you can see that there are different features. And if we look at the composition of the interstellar material, 90% of these particles are in fact hydrogen atoms or molecules, right? So that is important. And 9% of the particles are in the form of helium atoms. So you have hydrogen and helium, and all other elements, all other remaining elements is make from the remaining 1%, right? So astronomers normally refer to these elements as metals. So these 1% is actually metals, and this includes normally oxygen, carbon, nitrogen, iron, those kind of things, right? And if you consider component wise, so this is how the composition, but if you consider about the components that the interstellar matter made of, there are basically two components. Number one is gas and number two is dust, right? Those are the two main components that we have to talk when we are talking about interstellar matter, right? Now for the gas, interstellar gas consists of mostly from individual atoms, and the size of these atoms typically zero point 0.1 nanometer in terms of its size. Now hydrogen atom are the most common, by the way, And the gas contains some molecules. These molecules are tightly bound group of atoms. As an example, water, which is H2O, consists of two. I mean, this is just an example you already know, right? So this is just to, since I am just introducing molecules, H2O is a molecule, right? You all, I think I don't have to mention it here. You probably know about that. And these molecules are typically in the size of 1 nanometer. So you can see it's compared to these atoms, it's a bit larger. And most common, now this is important, the most common uh, molecule that you have in interstellar matter is molecular hydrogen, right? So just keep that in mind, right? So let's look at, that's about the interstellar gas. For the interstellar dust, we have interstellar dust normally consists of clumps of atoms and molecules again. So they made up of mainly elements such as silicate, graphite, iron, and also dirty ice. So that's kind of the composition or what's how the interstellar dust is made of. And these solid dust particles are typically in the size of 100 nanometers. And you can see they are a bit larger, and they are actually similar to those that make up smoke, fog, or haze on Earth. You know that when you have this fog or smoke on Earth, how it looks like, right? These dust particles act in a similar way in the space, right? So that's what I want to mention here, right? Now, if we look at the overall properties of this interstellar matter, without considering one by one, both gas and dust that you see in the interstellar matter seems to be very cool, and typical temperature of these uh, gas and dust particles are around 100 Kelvin. Now, if I convert it into Celsius, you know that it's around minus 173 Celsius, right? Uh, However, there is an exception for this. When you have interstellar matter close to hot stars, they get heated up because of these hot stars, and then the temperature can go up to 10,000 Kelvin, right? Right. Then let's look at about the gas. Now that's about both gas and dust. They are very cool in terms of their temperature, except one factor that if they are very close to a hot star, they can get heated up to 10,000 Kelvin. And if you look at the interstellar gas, they are actually very sparse. So what that means is they are not that much dense, right? The number density is about 10 to the power 6 particles per cubic meter. It seems that this number is higher, but if you compare this with air, air has about 10 to the power 25 particles per cubic meters, right? So that's why we used to tell that interstellar gas is very sparse. So that's like the proper word to mention it, right? Uh, if you look at interstellar dust, we used to tell that it is extremely sparse, right? So this is very sparse and this is extremely sparse, which means it should be even less denser. And the number density of this interstellar dust is actually 10 to the power minus 6 particles per cubic meter. So you can see that how less dense this is, right? Now, if you compare this with gas, this is about a trillion times less dense than the gas. So you can see that the dust particles are less dense. And if we compare this with relative to the air, interstellar matter is still very dusty, right? Even though this it seems to us that this density is low, it is very dusty still if you compare it with the air, right? Now, I have a question for you. Uh, Now, when you look at the sky at night, you can see that there are like large number of stars, right? Isn't isn't there a possibility that these stars can collide each other? Can it happen? How about the probability? Is it possible? What do you think? Do you have any idea about that? This is like a question that normally you may get one day from a kid, right? When you look at these stars, we know that they are moving here and there. There are like we used to tell that there are millions of stars up in the sky, right? Is it possible that these two stars can collide one day? Or
Yes,
is
I
it?
think so, sir.
You think so? Why is that?
Because there's an article,
Uh-huh.
and I according to that readings,
Mm-hmm.
I saw that there's two stars. I can't remember the name of those two stars, but
Okay.
those two stars form into one.
Mm-hmm.
Then and still we can see that combination in that particular galaxy.
Okay. Thank you for that information. And I would appreciate that if you can send me a link for that or something like that so that I can look at that as well. But
I'm
uh,
afraid so. It's but I couldn't get that link.
okay.
I saw it from the article that is given by uh, browsers, Google Chrome browser. There are some articles every day they use us to read. Under
Okay.
one of that articles, I saw that. Thank you,
Okay.
sir.
So thank you so much for that information. And just check. You can check. Others can check as well. With if you have find something like that, just send that to me as well. It should be interesting. But under normal circumstances, what I would expect is it is very less probable that these, I mean, this is also possible what he tell that, but in terms of the probability, it is very less probable that these two stars can collide each other, right? The reason is actually right here. What he has mentioned is actually maybe an exceptional case. It is possible in very rare cases, but under normal circumstances, it is like not as common as you think, right? So, so I have mentioned here that though the density is low in interstellar matter, total mass is substantial as the volume of space in which the such matter is found is huge, right? We know that as you saw the numbers in previous slides, that the density is very low in interstellar matter. However, uh, the volume of our space is huge, right? Because of that, uh, we have enormous amount of matter there. Now, what is what I want to emphasize here is that compared to stars, it is important to note that the stars only take a tiny fraction of volume of the Milky Way, right? So this is what I want to emphasize for you, and this is one of the reasons actually I have asked whether it is possible to have collisions between two stars. And this reason that it is very rare is because stars, even though you went outside and when you look at the sky, you see a lot of stars, but the reality is that it only takes very tiny fraction of the volume of the whole Milky Way, right? Which means the stars are actually apart from a very large distance, even though you see a lot of stars on the sky. And uh, now, the simplest example that we can think of is that we know that light only take about 4 seconds, maybe 5 or 6 seconds, I can't remember. Let's say 4 seconds to travel a distance equal to the diameter of the sun. Yes, so it's a diameter of the sun, right? So it only take like let's say 7 minutes to travel for us, right? For the sun. But the next star that we know or that is closest to us normally take how many years? 4 years to travel from sun to the nearest star. Right? If you think about the distance between these two stars, the light take 4 years to travel from one star to the other star. And you can see the amount of distance in that way. Right? It's a huge distance, right? Now this is why we think that it is very less probable that these can collide each other, right? So this, yeah, very like distribute in a huge volume and they are apart from each other from a huge distance. I mean, this is just a simple thing that I ask. I mean, just sometimes these kind of questions arise, right? I remember that I had this question even in one of my, uh, I guess, in progress meetings or something like that, from one of these professors who were doing astronomy when I was doing my PhD. So I was thinking about this at that time, and I mean, nobody has asked this from me before, so I thought that maybe it's interesting to discuss about that. Right. So just to give you an idea how these things work, so I have put here an example to estimate the mass of interstellar matter in our galaxy. Right. This is just a simple calculation. You don't need like Einstein's knowledge to calculate this. The only thing that you need is to understand that to have to calculate the mass, uh, that is basically volume times the density of atoms and then the mass per one atom, right? So this should give you uh, the total mass in our galaxy, right? And as I told you, it is only the tiny fraction that takes by the stars. So the most of the other atoms that I am going to that I have here as the interstellar matter will take the most of the mass from the galaxy. So this is why we can estimate mass for the galaxy in that way, right? Now I have given the example here. Suppose that the average density of hydrogen gas in our galaxy is 1 atom per cubic centimeter, right? So there is 1 atom per cubic centimeter. Each hydrogen atom has a mass of 1.7 times 10 to the power minus 27 kilogram. Now, if I assume our galaxy has a cylindrical shape with a diameter of 100,000 light years and a height of 300 light years, what is the mass of the gas? Right. So this is the mass of the gas, which we think that roughly the mass of the gas in our galaxy. Right. And the next question is, you will see that in our next lectures that this interstellar mass is what actually responsible to make these stars, because they are the raw materials, so they will be converted into stars. The next question is, how many solar mass stars could be produced from this mass of gas if it were all turned into stars? This will not happen, like all the interstellar material will not turn into stars. But if you assume that if all this material turn into solar mass stars, so I have given the mass of the sun here, then the question is how many stars this amount of interstellar material will be able to produce, right? Now this needs a small calculation. uh, shall I give you some time to try yourself? So just take few minutes and just try yourself to see how it works, because if I straight away show you the answer, then you don't get anything. So let takes few minutes and you can try yourself to get an answer. So I just need a number at the end, right? How many stars can be produced from this mass? You don't actually need any specific knowledge outside what I have mentioned here. So just have a try. If possible, give me an answer to the chat window. You can talk as well. And I will wait for a few minutes. Just should be interesting for you to try that. And then we will discuss after that. Right. I guess uh, this is Janit who shared this article, and thank you for sharing this, which is a very nice article. And if this is yes, Janit, if you need to talk about something,
No, sir. I just browse, sorry, Google that article
okay.
whether it's in the topic, but I just put in the group.
Okay. So is this the article that you talked before as well? Or
Yes, sir, but according to the image that in my memory was difficult, sorry, different with this image, but there were two stars colliding with each other and forming a single one star.
okay.
So I don't
Uh,
know.
Okay, so according to that's fine. It's okay. I mean, there are possibilities actually, and this particular article, I just went through the article that you sent me. This is actually a good thing that you. It is good that you share this with us. This article is about colliding two galaxies each other, not two stars. Now, actually, what happens is when you have two galaxies colliding each other, stars are inside galaxies, right? This is exactly what I actually needed from you. Now, sometimes students think that, okay, the two galaxies collide and you have billions of stars inside one galaxy and you have billions of stars in the other galaxy. When these two galaxies collide each other, then maybe the stars are the what actually collide each other, right? So this is what sometimes you think, but the actual case, this is not the actual case. What actually happens is it is the interstellar matter actually uh, most of the time that involves, and stars are actually it is very rare that stars collide each other. I mean, we don't tell that it doesn't happen, but it is very rare. The reason that your article itself actually mentioned it here.
Yes, sir.
So
I
it's
saw it.
yes, so it says that it is very rare that stars are colliding each other due to the large distances that you have in between. And I would recommend that all of others probably you should read this about this. Maybe I will post this into the Google Classroom myself. Seems to be a very nice article, which clearly explains what we need exactly at this point. Right now, for the question that I gave, so I am not sure whether you have, because this involves some calculations that you probably need the calculator. Let me, if anybody else found an answer, you can post it here. Maybe I will wait for another 2 or 3 minutes if anybody needs to have an answer. If not, we will together. I will share the calculation that I have. Probably you can see it then. There is a calculation that I have done. Let me try to get it shared with you. Right. So here is the calculation. I assume that you probably can see it right now. So I have already done the calculation. So I will explain what I have done. Uh, this is very simple. So the first assumption is the total mass is given by volume times the density of this. That is not an assumption. So that is the equation. Volume times the density of atoms times the mass of the atom. And then what you see here is actually I have converted light years into centimeters. Right? One light year is how many centimeters, right? So I have converted that, and then I assume that our galaxy is in cylindrical shape, and the diameter is given. So I got the radius as the half of the diameter, which is 50,000 light years. And the height is 300 light years, which is given here. And then this, I can use this information to calculate the volume of the cylinder. So which is this equation, that is phi r squared h. And so I have converted everything into centimeters here, just to make things easy for the calculation. And the volume of this cylinder, or in this particular case, it is the volume of our own galaxy. You have 2 times 10 to the power 66 cubic centimeters. Then you have to find the mass. So now you know the volume, which means now you have this value right here, volume. And then the density is 1. Uh, Density is given, that is 1. And then the mass of the atom is given, so that is this value right here. And just by multiplying each of these quantities together, you get the mass of the interstellar matter, that is 3.5 times 10 to the power 39 kilogram, right? So I expect that even in an exam that you should be able to do these kind of simple calculations, right? And then the next question is actually is even simpler, that you have this much of mass. If one star is mass of one star, which is equal to our sun, is 2 to the power 2 times 10 to the power 30, which is this one right here. I just ask from this mass how many stars that we can have. So this is roughly, you just divide the mass by the number of mass of one star to take the number, right? You know these simple calculations. So then your answer is this one right here, and this is roughly like equal to, you can say, 2 billion stars, even though it's not the same. It's, I mean, you can roughly tell that this is the correct answer. So it will be roughly 2 billion stars, right? Not exactly, right? So this is how you do this kind of calculations, right? Right, now let me go back to the presentation again. Right, so you should be able to see my presentation again. And so let's discuss few other slides, and then at the end, we probably will be moving on to our talking about how to do this practical, small practical assignment. Right, that's about interstellar matter. And then let's look at this particular image. So this is how the gas looks like near a hot stars, right? And this image is from the Orion Nebula. And I just put these two pictures just to give you an idea, like the Orion Nebula, which is in the left-hand side, is actually taken by, I guess this is from the Hubble Space Telescope, right? The one in the right-hand side actually taken by myself from the Kitwick National Observatory using a 0.9 meter telescope. And I expect that from the previous knowledge, when I tell 0.9 meter telescope, you should get the idea that this particular telescope has a primary mirror with a diameter of 0.9 meter, right? So this is just using, as far as I remember, a red filter or something like that. And so that's, I just put the two images just to explain this thing about what happens near hot stars, right? If when you have very hot stars, so they are able to heat the surrounding gas to temperatures closer to 10,000 Kelvin. And we have, in fact, I have mentioned this earlier in one of those slides as well. And so at the same time, what happens is when you have these hot stars, they emit a lot of ultraviolet radiation, and this radiation is capable of ionizing this hydrogen. Right? And at a typical moment, if you take a certain moment, most of the atoms near these hot stars are actually in the ionized state. because of the hot stars emit ultraviolet and they will ionize the surrounding gas. And it is actually also important that to note this that the detached protons, they may capture free electrons and become neutral. It can happen as well, can become neutral hydrogen once more. Sometimes some of the students used to ask that why this one, the one in the right hand side seems to be black and white, and the image in the left hand side is colored. I mean, that's just because the one in the left hand side is just processed by them using maybe different filters. So what I have is just the raw image that I took directly from the telescope, right? So that's it. So it is actually not a processed image. And I just need to mention, I just forget to mention that uh, in real situations, this is actually what we get from a telescope. And what you see actually in the internet is these color images are actually processed images sometimes, right? Now here are some more information, like we often characterize a region of space according to whether its hydrogen is neutral or ionized, right? So this is if you have a cloud of ionized hydrogen gas, we used to call it as a H2 region. Now, close to these hot stars, we normally used to have most of these H2 regions, which means this uh, hydrogen is basically ionized. So that's why we used to tell that H2 regions. Now I have put inside brackets in small letters here that the Roman numeral 1 is used to indicate that the atom is neutral, and successively higher Roman numerals are used for uh, higher stage ionization. H2 thus refers to the hydrogen that lost one electron, right? And Fe3 means, for example, ion that has lost two electrons. Actually, the reason that I have mentioned here it is the maybe students who are doing chemistry may have different way of using this ionizing, right? Which I am not familiar. But for the purpose of astronomy, we just use this convention, right? Just keep that in mind. Sometimes these things may differ a little bit from subject to subject. And so what actually happens is during a transition of electron captured by this hydrogen atom to the lowest level, they emit energy in the form of light, right? So when you have this ionized hydrogen, so they once they go into these ground states, they emit energy in the form of light. And generally this light actually correspond to this very red hydrogen lines, which is the strongest in and this is why actually these H2 regions looks red. Now this particular image that you in the left hand side, you can see this lot of red color, right? So that is why it looks red. And the one actually that I have taken from the right hand side, it is actually using a red filter, which I remember. So that is why the image looks very intensive using a red filter. Right? It seems to be its look in terms of the color. It actually looks black and white, but it is actually using a red filter that I have captured this way. So just you when you visualize, you give different colors now so that it's easy to visualize. But this is one in the right hand side is also using a red filter. Right. So that's about ionized hydrogen. And so I will stop actually talking about these things more because I have a lot of, if I'm going to talk, then the time wouldn't be enough. So then let's move on to the neutral hydrogen. Now only a small fraction of interstellar matter is actually close to these hot stars, right? You can as remember that I mentioned that the stars are very far away from each other, right? And because of that, there is only a small fraction that is close to this interstellar matter, right? To ionize them. So which means the most of these hydrogen actually are non-ionized, so they are neutral hydrogen. Now you can detect these ionized hydrogen easily because the ultraviolet photons from ultraviolet radiation from these stars actually ionize the hydrogen and they emit this red color or red lines. But for the neutral hydrogens, we don't have such thing, right? Most of the volume in the interstellar matter, in fact, is actually neutral hydrogen, and neutral hydrogen atoms, they don't emit or absorb light in the visible part, right? But however, they actually have some of the other elements uh, absorb visible light even at typical interstellar temperatures. Right, so this is just an example what happens in this space. You can see in the right hand side there is a star, and the star has these broad absorption lines. The absorption lines are a little bit broader when this light goes to, because when you are observing from Earth, what happens is actually this light has to go through these interstellar clouds, right? Because interstellar matter are more available, right? You can't, it's hard to avoid those when you observe something from Earth. So the light travels through this interstellar dust cloud. So what happens is when there is significant amount of this cool interstellar matter, so we know that the interstellar matter means basically the gas and dust. So they are sitting between us and a star. We will be able to see some absorption lines of the gas in the star's spectrum, right? And so they will absorb, the interstellar matter also absorb some of the light from the star, right? So, but we can distinguish these two kinds of lines because the star's absorption lines are a little bit broader. However, the from the interstellar dust and cloud, when they absorb lines, their lines are a little bit narrower. So on the right hand side, I have mentioned, shown you that few of the lines that are narrower, which were not available in the left hand side spectrum, right? So those narrower lines are coming from actually due to the absorption from the interstellar cloud, right? So that's how you normally figure it out. Uh, Now, as I have mentioned in the previous slide, there are some of the strongest interstellar absorption lines are produced by the calcium, sodium, uh, and many other elements can be detected as well in sufficiently sensitive observations. Calcium and sodium lines are in fact very prominent. And while these and similar observations proved that there was interstellar gas, they could not yet detect hydrogen, right? So the most common element due to its lack of spectral features. Now, we know that this inside this interstellar cloud, there are a lot of hydrogen, right? Not ionized hydrogen. Ionized hydrogen you can detect, but the hydrogen that is not ionized, they are available. But from these spectral features, actually what we are seeing is not the neutral hydrogen. What we are seeing is this calcium and those kind of things, right? And because of that, we should have a method to detect these neutral hydrogen, which is the most widely available component in this interstellar cloud, right? So here is the method to detect that. There is no other way of detecting it. And you, if you have heard this, you probably, if you sometimes, if you look at articles in the internet, sometimes you may come across with this popular word 21 centimeter line, right? So this is basically used to detect this neutral hydrogen in astronomy. This is like a very basic thing in astronomy. And so what actually happens here is, you know that in hydrogen atom you have an electron which is in the orbit close to the nucleus. By the way, this is, I'm not talking about quantum mechanics here, right? So just an explanation. Uh, so basically what happens is the proton and the electron may be spinning, right? And this spin can be towards two directions. As you see in these two pictures, A and B, it can be in the same direction or in the opposite direction, right? But when this electron flips over, if it changed its direction, so then because due to this particular flip, the atom can gain or loses a tiny bit of energy, right? And this is by this energy is gained by either absorbing or emitting some kind of electromagnetic energy, and this emitting or absorbing energy is actually correspond to this wavelength of 21 centimeters. So that is why this is used to call as 21 centimeter line, right? And this particular feature is actually used to detect these molecular hydrogen, because there is no any other way of detecting it, right? So here is the Harold Evan and Edward Purcell, and they are actually the pioneers of detecting this 21 centimeter line. And because this was very challenging, as you see it, right? Direct detection of hydrogen atom was very challenging, as the telescopes need to be capable of detecting very low energy changes, right? This change is very small. Uh, Now this Dutch astronomer called Henrik, he is the one actually who predicted that the hydrogen would produce a strong line at wavelength of 21 centimeters, according to the theory that I have explained earlier. However, the probability that a single atom will emit a photon is very low, right? If you consider one particular atom. But you know that, as I explained now throughout these lectures, there are so many hydrogen in interstellar matter. Is, it is the mostly available thing, which means yeah, the neutral hydrogen is very widely available, right? So there are so many hydrogen atoms in a typical gas cloud, so that collectively they expect that they will produce an observable line at 21 centimeters. So that was the prediction, and actually they have detected, and this is how the 21 how the entire sky looks like when you look at it from 21 centimeter line. And actually they have detected it, and that is how we normally detect this neutral hydrogen, right? And then ultra hot interstellar gas is my next slide. Now remember that we have talked basically about the interstellar matter today, and I told you that there is gas and dust basically, and we discuss the components, what are the components that we have in dust and what we have in the gas, and basic features. And then we talk that we have like ionized hydrogen and molecular hydrogen, and ionized hydrogen can be detected by its red line, but for the molecular hydrogen you cannot detect it easily. And this is where you use the 21 centimeter wavelength to detect the molecular hydrogen, right? So that's what we discuss up to now very briefly. And some of the interstellar matter, now in this slide, I would like to introduce about the ultra hot interstellar gas, which is that some of this interstellar gas is at a temperature of million degrees. So we have found that. So this is something that we did not talk before, right? Some of this interstellar matter that is found is at temperatures of million degrees, which is a very high temperature. And this is why we have this name called ultra hot interstellar gas, right? And uh, the telescopes that we have launched in the above Earth's atmosphere have obtained these ultraviolet spectra that contain these interstellar lines produced by oxygen atoms, and that they have been ionized 5 times. When you have something that has, if it needs to be ionized 5 times, that means you need a lot of energy for that, right? So this is why they this is actually how they detected this ultra hot interstellar gas. And then after some subsequent observations with X-ray telescopes, they revealed that the galaxy is filled with these numerous bubbles of X-ray emitting gas as well. Normally, if the gas is emitting X-rays, that means is that particular gas is very hot, right? So just look at the X-ray wavelength, and you can look at the temperature, converting to temperature. Normally, X-ray is very, very hot. So to emit X-rays and to contain oxygen atoms that have been ionized 5 times, the gas must be heated to temperatures of million degrees or more. Right? So that is the conclusion. So there are two observations. We have observed X-rays, and then we have observed that oxygen atoms that have been ionized 5 times. So from these two observations, we can claim that this gas must be heated to millions of degrees in order to observe these two things, right? Now you can see that in astronomy, you can't go and touch objects, right? So this is how actually astronomers make conclusions. You send telescopes or you observe through telescopes, and from the observations, you combine your observations with the physics knowledge that you have about the electromagnetic spectrum and everything, and then you conclude, okay, this temperature should be this much, right? So there is a nice like scientific method here. And now then what happens is then they go into next step, right? So next step is they have now predict what should be the reason for this, because up to now we have talked about interstellar matter. We never had an issue with uh, interstellar matter which have these enormous temperatures. Now we detect something like that from our observations. Now we have to explain it, right? So this is how the scientific method works. And then astronomers actually now predict that this remarkable temperature comes as a result of supernovae explosions, right? And supernovae explosion means actually an explosion of a star at a particular point during its lifetime. And there are two types of supernova explosions, type 1 and type 2, and they are also subcategorized as well. And we will, I'm not going to talk about that in too much details now because we will have a section about that, right? And what happens in a supernova explosion is actually they launch gas into this interstellar space. Basically, the after supernova explosion, the star will destroy depending on how it happens, right? Supernovas is actually a different field of study, so I cannot like explain it from one or two words. But what will basically happens is at a supernova explosion, this gas will be ejected into space at a very high velocities, and these velocities will be thousands per kilometer seconds, and this will be like 30% of the speed of light, if I tell it in that way. And when these galaxies, then when this ejected gas collides with interstellar gas, they produce these shock waves that heats the gas to millions of 10 millions of degrees. Now this is how we explain it to now. And here is just an example. This is called Vela supernova remnant. Supernova remnant is what is remaining after this huge supernova explosion. And we believe that this happens about 11,000 years ago. And this is a dying star in the constellation of Vela. And this has exploded and then becoming a bright as full moon in Earth's skies. So this has happened at around 11,000 years ago, but you can see this faint round filament kind of structure in right in this image, right, from some points to the other points. You can see that filament kind of structure, and this is the edges of the remnant that are colliding with this interstellar matter medium and heating the gas as they plow through through to temperatures of million of Kelvin, right? And so just an example what we have talked before. And then right, and then uh, I guess some of your mic is on and I can hear that some of you are talking, right? So I would appreciate that if you are talking something not related to the course, maybe you can unmute your mic. And right, so uh, about molecular clouds, again, astronomers have observed these very complex molecules in the interstellar clouds as well, using the spectra in radio and infrared wavelength. We did not talk about that before. And And this discovery of molecular complex molecules in the space actually came as a surprise because most of the interstellar space is filled with ultraviolet violet light from stars, right? So once you have this ultraviolet, this light is capable of disassociating these complex molecules. So which means we normally don't expect to have complex molecules. However, the space contains significant amount of dust which is capable of blocking out this starlight. So once the starlight is blocked, that creates a space for have these complex molecules in molecular clouds. And also the gravity also help for this process as well. And here is an example. This is called Bernard 68, and this object is cataloged by this E. Bernard, and this is the dark interstellar cloud. So this is striking appearance that you see as a dark region is actually due to the fact that it is relatively close to the Earth. That is one reason, which means there are no bright stars between us and it, right? That should be the first condition. And then at the same time, it's the dust that it contains obscure the light from stars behind it, right? So if you have stars in front of it, you cannot see it, right? You can't do anything for that. But when it is close by, we don't have stars between this region and us, and all the light coming from the behind is blocked by the dust, because dust absorb all these ultraviolet light coming from the stars behind it, right? And here are some of the interesting interstellar molecules, which are like we seems to believe as some like complex molecules. And you can see this ethyl alcohol, benzene, acetic acid, all things are there, right? Right. Now here is another image of, now here is how you detect. Now I told you that clouds and dust both are in the interstellar matter, right? What we have talked up to now is detecting molecule gas. Right. Now here is a way of detecting dust, right? So to detect dust, you have to look from a different wavelength, basically, right? Because dust clouds actually they in the space, so they betray their presence in several ways. One is blocking the light from distant stars. So one, they block the light from distant stars, and they actually emit energy in the infrared part of the spectrum, right? Which means if you look that particular image through infrared wavelength, then you should be able to see this, right? So that's the idea. And the picture that you see here is the Horsehead Nebula. And this nebula is the one in the right hand side. The picture A is actually, this is by the way a dark cloud, one of the best known images in astronomy, which we call it as the Horsehead Nebula. The picture in the right hand side A is taken from the visible light. And you can see that these dust clouds are especially easy to see. Again, when you have this bright background, you can see a lot of these dust clouds. But when you look at the image in the right hand side, it is taken from infrared radiation images, right? Infrared radiation, which means the image looks more clear because you can look the dust clouds through infrared. So that's what I want to tell here, and all the details about the image actually mentioned in the below, which you can read through, and I'm not going to explain all the information. Anybody knows what is this? This is actually what we call as the Pleiades star cluster, or this is kind of popular among us as Seven Sisters, right? This is a star cluster, and this is an example of a reflection nebula, right? And just read through the information here. You will see what it actually means. So actually, there are some dense cloud of dust that are close to luminous stars, and uh, and they scatter enough starlight to become visible, right? So when the light coming from the stars And once you have these dense clouds of dust, so what dust is, this light will be scattered from the dust, right? So then they will be visible. And this is what happens in the Pleiades star cluster. And this the bluish color that you see surrounding the stars in this image is an example of a nice reflection nebula. And this seems to be really blue in color. If you look through a binocular, actually, you can see this very clearly. And not the nebula, in fact, but you see these bright blue stars. And just to give you some information about this particular star cluster, this is around 400 light years from us. And we used to tell that we used to name this cluster as seven sisters, but that does not mean that there are only seven stars, but there are seven bright stars that you can see from your naked eye, but there are a number of other stars inside the cluster, right? And what you see here is actually the Pleiades cluster is currently passing through this interstellar cloud, which contains a lot of dust grains. So what happens is the light from the star hits to these dust grains and then they scatter. Right? So that is what you see in this image. And I have mentioned here what is the reflection nebula, which you probably may be able to read, or maybe I will take this one, two, three slides. So let me finish this then. Right. So the reflection nebula is basically when you have interstellar matter, uh, which is often found in the vicinity of very young stars. The light from these stars may be scattered and reflected by the dust particles. I guess I have mentioned this in the previous image. And the dust particles scatter the light in the same manner that particles in the Earth's atmosphere. You know that scattering of light in the Earth's atmosphere, right? And so the same thing happens here. And the result of this scattered light, these young stars, often surrounded by bluish clouds of interstellar matter called reflection nebula. Just read through it. I think you can understand this now, right? So I just explained it. And there is a feature which we called as interstellar reddening. So what happens is that when interstellar dust grains absorb a lot of starlight, and half of this starlight, at least half of the starlights that can interact with dust also scatters, right? And both absorption and scattering makes stars look dimmer. The effect of both processes are called interstellar extinction. And this is something I expect that you probably should remember if I ask what interstellar extinction means. Actually, that is because uh, the star seems to be dimmer because of the absorption and scattering process due to dust particles, right? So you have a lot of these dust particles, they either scatter or absorb the starlight, so which makes these stars looks dimmer for us. Now, if you just go for do some kind of astronomy research in future, you will hear something called extinction correction among astronomers. So what they actually do is there are experimental and methods that we have derived to make a correction for extinction. Because let's say you are looking at some galaxies outside, like maybe millions of years away from us. So when this light comes through the space, all these light face to this particular problem, right? Interstellar extinction, which is absorption and scattering of light due to the dust particles. So which means when you measure the magnitude or the brightness from Earth for any of these objects, assume that you are measuring a brightness of a star. Now what has actually happened is this light has to come through the interstellar matter. You know, when it comes through from this dust particle, they either absorb or scatter some of this light, which means when you measure the brightness from Earth, you are not measuring its actual brightness. You have lost some of the data because of this particular process called interstellar extinction. So what you have to do is then you have to make a correction for that, which I will not talk here, like how to do corrections and everything, but just get the idea, right? And light from these hot stars actually, this phenomena is also known as interstellar reddening, by the way, right? That's because actually as a result of this extinction, some stars look red, uh, even though their spectral lines indicates that they must be extremely hot and blue, right? And this is a problem actually the astronomers have right now, and we are doing some corrections for this because of this absorption of some of the lines. Because when you uh, consider about the blue and red, blue used to scatter more, right? I guess you know about this, which means you will get more of the red light. So sometimes if you don't do a extinction correction, then you used to wrongly predict maybe a star may be red, and then you predict something based on that, which is wrong, right? So you have to do this correction because of that. So like as I have mentioned here, as the result, some stars look red even though their spectral lines indicate that they must be extremely hot or blue in color. Now light from these hot stars is not only dimmed but also reddened by interstellar dust. So that's because of that reason. And when it is reddened, we used to call this particular process as interstellar reddening, right? And the same image that you see right down in this presentation is the same Bernard 68, and how it looks like when you look through infrared. And you can see that when you look at the same uh, area through infrared wavelengths, then you can see all these stars that you could not see from the visible light, right? That's what infrared can do you, right? And this process I have, since it is important, I have mentioned here what extinction means. The sunlight will absorb as a result of this process called extinction. So if there is enough intervening matter, all of the light will be absorbed, leaving a dark region on the sky, right? So that's how these dark regions are made in the sky because of this extinction effect, right? I guess you have a few slides. Now the last slide is about, now we have talked up to uh, more details about interstellar matter and interstellar composition of interstellar matter and how you detect it, and what are the components and how it looks like through different wavelengths and those kind of stuff. Right now, at the end, to finish this particular lecture, so I just briefly go through the last few slides. So just read through those. So I guess you can understand it, right? So if you have questions, you can ask at any time. And now we have discussed about the formation of stars from interstellar matter. Now we have to see what is the difference between the interstellar matter and stars, right? So that's how we scientifically approached the process or a question. Now we have stars, and we said that there is interstellar matter, which should be the raw materials for providing or making stars. Now we have to look at, okay, what is the difference between interstellar matter and stars? So what specific things that has met by interstellar matter to become a star, right? So that's what we are going to look at from the next lectures. So what we know now is both are composed similar mixture of elements, but also we know that the star is so dense, and that the pressure in its center creates temperatures hot enough to burn hydrogen. So these things actually what where we will start. So that is the difference between interstellar matter and star. Both have similar elements, but a star is more dense and its temperature is very hot that it can burn hydrogen, right? So we know that there are hydrogen, most of the composition is hydrogen in interstellar matter. And interstellar clouds actually not dense enough to do this, which means the burning hydrogen, right? So let's start from here. The next lecture, we will talk about what are the conditions that should be satisfied by the interstellar matter to become a star, right? So that will give the birth to the star, and we will continue from there how what happens after the birth. So they will become like neutron stars, black holes, those kind of stuff, right? Right. So now the time is 7:20. So let me just go through that very briefly. I will go through that session that I have showed to you. Right, so I'm going to finish the lecture from here. Right, so what I have, so I guess, right, so there are some information that is given by, I guess this, I'm not sure whether I am pronouncing your names correctly, so sorry about that. I guess Syotami, if I don't know whether I'm, so thank you for that. And so there are some information that she has shared as well. So let me check this information. Yeah, this is about a neutron star. You can go ahead and look at that as well. Uh, which we will talk about neutron stars as well, right? So that will come future, because all these things that you see in the news, you will understand at the end is actually something that happens in a lifetime of a star, depending on its features and properties, right? So you will realize it. So that's why everything that you get in these articles, most of them are actually connected what you will be learning in the course. Right now, I need to show you something that, so let me take, so remember that I have put a small assignment for you. Okay, let's do it in this way. So I will just look at the assignment and see what you can find yourself about that. I will give you one or two links. One is actually this database, which I called as Sinbad. So let me give you the link for that. I guess I may have post this before as well. This is the link that you can go and look, search these stars. So there is an option called basic search, and if you type the name of the star correctly and search, it will give you all the information that they have about this particular star, and that information should have uh, like the brightness of the stars for different filters and some of the other information, what kind of a star that is, and maybe the spectral class. All this information is available, right? And what you need to do is select those. Now the number one is you have to go outside and wait for some time, like 15 minutes, right? I am not sure how you can do it depending on your location. Make sure that when you go outside, it is safe to go. And because of that, I don't force anyone to do this, but which means I am not going to add you marks or anything like that. But this is for your benefit. If you do this, you will get a good understanding, right? And it will be easier for your exam. That's the idea. But I am, because I do not have an idea that what kind of conditions that you are living and how is your surrounding. I am not forcing you to do it, because don't go to jungles or anywhere like that and to do this, right? You don't have to do that, but just go outside. And the four stars that I have given you are four bright stars that if you go around 8 or 9 outside, you can easily visible. Now, the first thing that you have to do is go outside on a very clear night. So you can take probably next 2 weeks to do this, right? Anytime. And then once you go outside on a clear night, you should see these stars up in the sky. And two of them actually belongs to the constellation Orion. And if you need to look at where they are, let me give you the link for that as well. So this should be interactive sky chart from the sky and telescope. And by the way, this is not the only way of doing it, but this seems to be nice. Uh, and I guess I have also mentioned you before that uh, stellarium software, you can use that as well. But from this sky chart, what you need to do is roughly mention your latitude and longitude. So you can Google map, from the Google map, you can find it. So what you can do is mention the latitude and longitude, and then fix that, and then you can fix a time. Let's say just fix it for like 9 p.m. or something like that. Then it will show up the sky that you see in a window like this, right? So the one that I have shared just with you, it is what you should see. So on the left hand side, you can see that you can set the date and time, everything. And I don't know whether you can see my mouse pointer. If you can see it, around 9 p.m., Beetlejuice and Regal both are in the same cluster. That's what I, and then Aldebaran is like here. So one thing I expect from you is go outside, look at the sky, and try to identify some of these star patterns and identify some of these stars, right? So that should be part of this. Because if you, once you, after you doing this course, with bunch of lectures, even if you don't know how to understand or how to look at a star, there is no point of doing this, no. So then just make sure that you go outside, and this is just for fun, right? So just go outside and wait for 15 minutes. So that's number one, right? Because if you don't wait enough, your eyes does not get adjusted to the dark, and you will not see anything. You will just see few stars. But if you stay for some time in the dark, your eyes get adjusted. So that's why I told you, make sure that your place is safe to do that. uh, and because there may be snakes and those kind of stuff outside, right? If, depending on your place. So make sure. And one thing that I can tell you is, if you have a red light with you, that will be very helpful, because the red light is what astronomers mostly use, because you can, the red light does not disturb you that much. Other lights disturb, but just have a small flashlight. Just go outside, don't go far away, just outside your home, and just look at the sky, right? So that's it. The reason that I choose these four stars is specifically because they are very around 8 or 9 p.m. They are up in the sky above your head, close to the zenith, so that easily visible for anyone, right? From any place. So you don't just go outside and look at the sky for like few 15 minutes and try to locate the four stars, and just see whether from the eyes you can see which star is more redder for you from your eyes, right? So this depends on, there is no marks or something like this. I just need to see how you observe and look at these stars, right? And just see how red these stars, and then align them to the order, and then you have to go to this database and check those, and then find this color of the star depending on their magnitude. And how to use the database and everything, I will show you in the next day, right? So as an initial point, just go outside and look at the stars, right? Now, the students who are not joining, just tell your friends to do that as well. Maybe they do not have, maybe they have issues of joining and so and so. So just ask them to do the same thing as well. Right, I guess the time is up for today, so I will stop from here. Next day, we will continue from this point, and you will not have classes tomorrow, but expect a class on Saturday, right, on the same day. So my plan is to finish all your lectures by 10th of February, and at the same time, I will be posting a tutorial for you with some of problems that will be helpful for you to understand what we have done up to now. So try to do that yourself as well. During the probably last one or two lectures, I will discuss all these problems together. So I will give you some time to work out yourself, and then if you have any problems, we can discuss it at the end. Right. So let me stop for now as the time is passing by, and thank you for giving all these suggestions and everything today. And we will meet on Saturday again.